Hello, student. So, in our previous week, we have seen that we can represent any uh, periodic signal. Okay, we can represent a periodic signal as a linear combination of complex exponential function. Okay. Any periodic signal with the period t naught, okay, can be represented as a linear combination of, okay, that means sum, okay, weighted sum, okay, linear combination of complex exponential function. Okay, so today we will see some further details. Okay, uh, so I think already you got this idea. Okay, any signal, any periodic signal can be represented as a linear combination of complex exponential functions. Okay, so we know that we have two basic periodic function. Okay, two basic periodic function. Okay, two basic periodic function. What are they? I think you can remember. One is sinusoidal signal. Let's say it is x1t. Okay, so sinusoidal signal is like that. So this is the sinusoidal signal. Okay, and other periodic signal is complex exponential signal. So we can write it as like this. Okay, so this one is a sinusoidal signal. Okay, and this one is the exponential signal, complex exponential signal. Complex exponential signal. Okay, I hope you can remember these two periodic function. Okay, these are the basic periodic function. Okay, so we have proved that the period of the sinusoidal signal is t naught to 5 by omega naught. Okay, and also for this complex exponential signal, the period is, let's say it's also t naught. Okay, it is 2 by omega naught. Okay, so for both signal, if the frequency is fundamental frequency is omega naught, the period is t5 by omega naught for both signals. Okay, so these are basic periodic function. Okay, so we learned that any periodic signal can be represented as a collection of complex exponential signal. No? Okay, that is we called actually Fourier series representation. So this is Fourier series representation. Okay. Okay. So if we write the identities for Fourier series representation, okay, we have these identities. Okay, I think you can remember that. So xt is a periodic signal, okay, with the fundamental period is T naught, okay. So we can write this signal as a sum of complex exponential terms, okay. So normally it is written as jk omega naught t, jk omega naught t, and here we have coefficients ck, and this k is an integer from minus infinity to plus infinity, okay. So k is an integer, okay. K can be a plus or minus integer that can be from minus infinity to plus infinity, okay. So we have minus infinity, so on, -3, -1, 0, so on. Then from 0, 1, 2, 3, 4, so on up to plus infinity, okay. So k is a plus or minus integer, 1, 2, 3, 4, like that, okay. So this is k, okay, and this is we called actually Fourier series coefficients, okay. This ck is the Fourier series coefficients, Fourier series coefficient, okay. And we can evaluate these coefficients using an integral. It is like that. Ck is equal to 1 by T naught. Okay, T naught is the period. Okay, so we already told that the period of this signal is T naught. Okay, okay, and this omega naught is also related with the T naught. This omega naught is equal to 2 phi by T naught. Okay, so this omega naught and T naught are related. Okay, omega naught is equal to 2 phi by T naught. Okay, so the integration should be done within a period duration T naught. Okay, and the integration, you have to do the integration by multiplying xt. That means your signal by e minus jk omega naught t dt. Omega naught t dt. Okay, so this is the identity to estimate the coefficient ck. Okay, actually these two identities we have seen in our last class discussion. Okay, and also it is better to keep this identity also, better to keep this identity also in your memory. That is, when the k is equal to 0, so you know that this k is an integer that can be from 0, -1, -2, okay, -2, -3 up to 0, okay, -t, -2, -1, -1, -1, -2, -3 up to infinity or plus 1, 2, 3 up to plus infinity, including 0. Okay, when you evaluate the 0th term, okay, 0th coefficients, okay, you can see that this k is 0, no? This k is 0. So if you substitute 0 here, it is j0 omega naught t. That means the about term will be 0. Okay, so it will be e to the power 0, and e to the power 0 means it is 1. No? So this integration will be within t naught only xt dt. Okay, so this identity to evaluate 0th coefficients. Okay, So this is the Fourier series representation. Okay, this is the Fourier series representation, and it is said that any periodic signal can be represented as a linear combination of complex exponential signal. Okay. Okay. So we have an example to do. Okay. But before the example, we will see some details about this Fourier series representation. Okay. So now you already so let me delete this one. Sorry. Okay. So we will see some details about this equation. Okay. About this equation, about these equations. Okay. So so if you have given a signal xt, okay, that is a periodic signal with the period is t naught. Okay. So if you have given this kind of signal, you can represent this signal as a collection of complex exponential function. No, so xt can be written as a collection of these exponential terms, but there is a weighted coefficients. Okay, so if you see that, so you can write this sum as like this. Okay, so this k from minus infinity to plus infinity. Okay, so you have some terms. Okay, you have some terms from minus infinity to plus infinity. Okay, then minus infinity to some terms plus. Let's start from, we can't write all the terms here because there are infinite number of terms. Okay, so we will write few terms to get an idea. Okay, so if I write some terms, okay, so let's say that k is equal to minus 3. Okay, so this k is from minus infinity to plus infinity. Okay, so it is minus infinity to minus 10,000, minus 100, minus 50, minus 40, like so on, minus 3. Okay, let's say k is minus 3. Okay, so that is, let's say the coefficients is at k is equal to minus 3. Okay, so here we consider the k is equal to minus 3. Okay, so let's say that the coefficients is c minus 3. Okay, then e j k is minus 3, no, minus 3 omega naught t. Okay, so this is one term. Okay, then let's say that k is equal to minus 2. Okay, so at that time this term will be minus 2 e to the power j minus 2 omega naught t. Okay, plus let's say c is the k is minus 1. At that time, minus 1 e to the power j minus 1 omega naught t. Okay, likewise, when the k is equal to 0, okay, k is equal to 0, it is c0, the coefficient is c0, and it is the other term is j0 omega naught t. Okay, so you can see that it is 0. all are 0, so it will be e to the power 0. Okay, e to the power 0 means it is 1, no? So this terms is not available, it is 1. Okay, and if you consider C1, that means K is equal to 1. Okay, so your other term will be J, K is 1. So this is J, K is 1, omega naught T. Okay, so if you say, let's say that K is equal to 2. Okay, at that time, your term will be C2 e to the power J2 omega naught T. Okay, plus when the K is equal to 3, it is C3 e to the power J3 omega naught T. Okay, so on, it will go up to plus infinity. Huh? I hope you can understand. Okay, so I just expand this term. Okay, nothing do any special thing. Okay, I just expand this term with respect to K. Okay, so you know that K is from 0, -1, -2, -3, so on up to minus infinity, and also 1, 2, 3, so on up to plus infinity. Okay, so when the K is 0, the term is C naught, and other term will be 1, so you will get only C naught. Okay, when the K is 1, that the coefficient is C1, and you have EJ, K is 1 omega naught T, and when the K is 2, C2 EJ2 omega naught T, so on up to infinity. And also from minus side, there are some terms. Okay, K is equal to -1, C -1, EJ -1 omega naught T, C -2 e to the power J -2 omega naught T, so on up to minus infinity. Okay, so this kind of collection we will get, no? So this is a collection of complex exponential sigma. Okay, so if we look at this carefully, you can see that this all terms have omega naught. Okay, all terms have omega naught. Okay, so if you consider this term, okay, so the frequency for this term is -1 omega naught. So this is the frequency for this term. Okay, and frequency for this term is -2 omega naught T. Okay, and frequency for this term is omega naught. Okay, and frequency for this term is 2 omega naught. Okay, and for this it is 3 omega naught, and 4 omega naught, 5 omega naught, 6 omega naught up to plus infinity. No? And also from here -2 omega naught, -3 omega naught up to minus infinity. Okay, so these are some frequencies. No, so these are actually frequency component. Okay, so we can say that. Okay, we can say that this xt, okay, this xt is a collection of frequency component. Okay, frequency component. Okay, but you can see that this is -1 omega naught, -2 omega naught, and this is omega naught. This is 3 omega naught, 2 omega naught. Okay, what is the frequency of this term? That is 0. No, the frequency is 0 here. Okay, that means it is 0 omega naught. Okay, so it is 0 omega naught, but here the frequency is 0. Okay, so you can see that these frequency are somehow related, no? Okay, so all these frequency terms have one fundamental frequency, that is omega naught. Okay, so all these frequency component has one omega naught. Okay, the fundamental period is omega naught for all these frequency components. Okay, that is one thing you should understand. Okay, so these are some frequency components. The xt can be write as a collection of frequency components. Okay, but they are related. No, they are related. Okay, they are related. Okay, actually these frequency component we called as harmonics. Okay, so these are harmonic. Okay, so that word is very important. Harmonic. Okay, harmonics. Okay, so these are harmonics. Okay, so uh, so if you consider this one, so this is C naught, only C naught, that is the frequency is 0. No, here the frequency is 0. Okay, so actually what is this? It is a DC component. No, it is a DC component. So there is no any frequency. No, it is a DC component. Okay, so it is a DC component. Okay, and that one is the 0th harmonic. No, 0th harmonic. So this is the 0th harmonic. That means K is equal to 0. So this is 0th harmonic. Okay, and this one and this one. Here the K is equal to -1 and here the K is equal to plus. So these two are first harmonics. These two are first harmonic. Okay, and if you consider this one, this is K is equal to -2 and here also K is equal to -2. So these are second harmonics. Okay, these are second harmonics. Likewise, this one and this one is third harmonic, and you have fourth harmonic, fifth harmonic, sixth harmonic. Actually, in here we have infinite number of harmonics. No? Okay. So these are harmonics, but they are related. No, related with the fundamental frequency. Okay, because all these harmonics has one fundamental frequency, that is omega naught. Okay, actually that is the fundamental period of xt. Okay, fundamental frequency of xt, omega naught. Okay, so I hope you get it. If you can't understand, if you couldn't understand still, please refer the textbook and try to understand this concept. If you couldn't understand, you can ask me again, then I will explain this again. Okay, so please try to understand this concept. Okay, so you can see that. Okay, you can see that any periodic signal, okay, any periodic signal is a collection of harmonically related frequency components. Okay, frequency components, and we call these also spectral components. Sometimes we called it spectral components. Okay. Okay. So another thing is that, okay, so this Fourier coefficients, sometimes we call this as, normally we call this as complex Fourier series coefficients. Okay, why we called it complex? Okay, because these coefficients can be a complex number. Okay, so I hope you can remember the complex number. I'm sure that you have learned the complex numbers, the concept of complex numbers in your mathematical module. Okay, so you know that complex number, any complex number can be represented as x plus y. Okay, so this is the imaginary part and this is a real part. Okay, so if this imaginary part y is equal to 0, so this c is a pure real value. Okay, so anyway we can represent any value as x plus iy, where if it is a real value, this y will be 0. Okay, so any number we can see as a complex number. Okay, so normally this ck we referred as complex Fourier series coefficients. Okay, but this ck can be a real value or complex value. Okay, but anyway we have referred it as a complex value. Okay, but it can be also real value. Okay, don't get confused. Okay, but if you can't remember the concept of the complex numbers, I recommend you to refer your previous note and try to refresh the memory of this complex number. Okay, because throughout this course we are dealing with complex number. Okay, most probably with complex numbers. Okay, so I hope you get this idea. Okay, so any periodic signal can be seen as a collection of harmonically related frequency components. Okay, okay, so another thing. Okay, another thing. Okay, you know the Euler formula. Okay, you know the Euler formula. What is Euler formula said? Okay, Euler formula means E j theta is equal to cos theta plus j sin theta, or E minus j theta is equal to cos theta minus j sin theta. So these are the Euler formulas. Okay, these are the Euler formulas. Okay, so you can see that any of this, all of these complex exponential terms, okay, exponential terms, okay, here it is minus j omega naught t, that means it is minus j theta form, okay, and these are plus j omega naught t, this plus side terms are j plus j some value omega naught t. Okay, so it is the form of, those are in form of this e to the power j theta. Okay, so all these terms can be written again as a cos and sine terms, no? Okay, so these terms, okay, once you write this series, okay, so this is a series, no? Okay, this is a collection of complex exponential function. So each complex exponential function you can write as a cos theta plus j sin theta, as a sinusoidal signal, as a collection of sinusoidal signal, sine and cosine signal. Okay, so you can see that any signal, any periodic signal, we can write as a collection of sinusoidal signal also, no? This xt also can be represented or written as a collection of sinusoidal signal. That means cosine signal and cos signal and sine signal. Okay, so actually this is the trigonometric Fourier series representation. Trigonometric Fourier series representation. Okay, so you can see that any periodic signal can be represented as a harmonically related frequency component. Okay, so that frequency component also we can written as a complex exponential function or sinusoidal function. So these two are the basic periodic function. No? Okay. So please get that idea. That is very important. Okay. So I will write that term here again. Okay. Please try to understand this concept. It is very important. Okay. So any signal, any periodic signal. Actually, this is not any. Okay. If you okay, any, I will tell it. Okay, any periodic signal. Okay. Actually, this any is not completely true. Okay. This is not completely true because actually the many signal, almost all practical signal, we can represent. Okay, we can represent it as a linear combination of okay, harmonically related frequency components or spectral components. Okay, frequency components. Okay, components. Actually, almost all the practical signals. Okay, we can represent like this. Okay, to represent like this, we have to satisfy some condition that is called district condition, as I can remember. Okay, district condition. Okay, let's see. I can't remember the name clearly, but is that one is not important. Okay, we can say that any periodic signal, but actually any is not completely true. Let's see. Give me a moment. So this is our textbook. Okay, and I think you can refer this one also for more information. Okay, so here you have the fifth one is a Fourier analysis. Okay, and this is the Fourier series representation, what we have discussed just now. Okay, so these are the two fundamental basic period. Okay, exponential and sinusoidal signals. Okay, and this is the complex exponential Fourier series representation. Okay, we have seen this one, and this is how we can evaluate the complex Fourier coefficients. Okay, so you can see that here also it is mentioned as complex Fourier coefficients. Okay, and this is for the zeroth component. That means now you know that this is to evaluate the DC component. No, okay, this is to evaluate the DC component. Okay, this Dirichlet condition. Okay, I can't pronounce. I don't know how to pronounce that. Correctly. Okay. Anyway, it is Dirichlet condition. No, if a signal satisfy this Dirichlet condition, okay, those signal can be represented as a linear combination of harmonically related frequency component. But generally, we can say that any signal, broad class of signal, can be represented like this almost all the practical signals we can represent like this. We can see as a collection of frequency component. Okay, harmonically related frequency components. Okay, so these frequency components sometime we can written in terms of complex exponential terms, or sinusoidal terms. Okay, so if it is complex exponential, we called it complex exponential Fourier series representation. And if it is sinusoidal, we called it trigonometric Fourier series representation. But we are mostly focusing on complex exponential Fourier series. Okay, so this is the idea you should get. Okay, so these are some harmonics. Okay, and this is the zeroth harmonics, that is the DC component, and the frequency is 0. Okay, and so this -1 and +1, k is equal to -1 and +1, that is our first harmonic. When the k is equal to -2 and +2, it is second harmonic, third harmonic, so on. Okay, so please get that idea. Okay, now we will move to our example. Okay, please keep that in your memory. Okay, so we will move to the example. Okay, so we are given a signal xt. Okay, and here we have to determine the complex exponential Fourier series representation of xt. Okay, so we are asked to find the Fourier series of this xt. Okay, so let's see how to do this example. Then I think you can get a clear idea about this equation, about this identity again. Okay, so you know that. So we can see that at a glance. Okay, to represent it as a Fourier series. Okay, this xt should be a periodic signal. No? So first we should see that whether this xt is periodic or not. Okay, periodic or not. If it is not a periodic signal, if it is a aperiodic signal, we can't represent it as a Fourier series. Okay, so so you can see that at a glance we can see that these terms will appear here again, and will appear here again, will appear here again. That means these terms are appearing repeatedly. Okay, in other words, this is a repetitive signal. No, the signal is repeated. Okay, so that means it is a periodic signal. No, so so this is a periodic signal. So xt is the periodic signal. So this signal should be able to be presented in a Fourier series. Okay, so this xt is a periodic signal. Periodic. Okay. Okay. So definitely we should be able to represent this as a series, no? Fourier series. Okay. So our next task is to find the Fourier, the period of this signal. Okay, so what is the period? Okay, so you can see that if you consider this point, okay, if you consider this point, it is repeating again after here, no? And this point again repeating after here. Okay, it is repeating after here. Okay. So you can say that this point again repeating here means this is the period. No, this is the period. So what is the period? It is T naught. So we can get this information by observing the waveform. Okay. So by looking at the waveform, we can also see the period of this xt. Okay. Period of this xt is T naught. Period of xt is T naught. Okay. So now we can write this as a Fourier series representation. Okay. So uh, so xt can be write as a sum of complex exponential term, and there is a coefficients also, and this k is from k is an integer, that is minus infinity to plus infinity. Okay, so this k can be 0, 1, 2, 3, so on up to plus infinity, and 1, 2, 3, minus 1, minus 2, minus 3, so on up to minus infinity. Okay. So we can write this xt. Okay. So we can write this xt. Okay. We can write this xt as, okay. So there are some component. Okay. So when it is minus 3, let's say it is C3 e to the power j minus 3 omega naught t. This is one harmonic. Okay. This is the third harmonic, no? Third harmonic components. Okay. And when the k is equal to minus 2, we have c minus 2 e to the power j minus 2 omega naught t. Okay. Plus when the k is minus 1, we have c minus 3 minus 1 e minus 1 omega naught t. When the k is 0, you have 0 e to the power j k omega naught t. That means k is 0, so e to the power 0, that means 1, you will have plus. Okay. Then when the k is 1, you have c1 e to the power j1 omega naught t. When the k is equal to 2, you have c2 e to the power j2 omega naught t plus c3 e to the power j3 omega naught t, so on up to 1 plus infinity. Okay, so you will have these terms. Okay. So this is the zeroth component. Okay, when the k is equal to zeroth component, and this one is minus 1, this minus is, this one is minus 2, this is plus 2, sorry, this is minus 1 and this is plus 1. Okay, and this is minus 2 and this is plus 2, and this is minus 3 and this is plus 3. Okay, so this is our zeroth harmonic. Okay, zeroth harmonic or DC component. Okay, that means the frequency is 0 here. So we have 0 frequency here. Okay, and this is this one, and this one is our first harmonic. Harmonics, no, there are two first harmonics. Okay, harmonics. Okay, harmonics component, first harmonic component. These two are our second harmonic component. Okay, these are our third harmonic component. These are our third harmonic component, and also we have fourth harmonic, fifth harmonic, sixth harmonic, up to infinity, and also we have minus. Here also we have third, fourth, fifth, sixth, so on up to minus infinity. Okay. So we can write this, because this is a periodic signal, we can write this xt like this. Okay. So what is our task actually here? Okay, we can write, no, we can write it like this. Okay, but here we have some unknown components. What is that? These Fourier coefficients. Still, these are unknown. Okay, so we have to find, or we have to estimate these Fourier coefficients, complex Fourier coefficients. So we can do it because we have a identity to estimate the Fourier coefficients. Okay, so that is Ck equal to 1 by T naught. The integration should be within T naught, within the period, xt e to the power jk omega naught t dt. Okay. So this is the identity to estimate this coefficients, Fourier coefficients, complex Fourier coefficients. Okay. So we will see how to do this. Okay. So this is our, so I will, so right, I will take this waveform here. Okay. Okay. So we have to do this integration within the T naught duration. Okay. So 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 the integration should be within T naught. That is the condition. Okay. The integration should be within the T naught. Okay. So you can choose any T naught duration. Okay. So you can do the integration from here to here. Okay. From here to here. That is, you have T naught time duration from here to here. Complete T naught is there. Okay. You can do it from here to here if you want. Okay. So at that 2 point, within that 2 point also you will have a T naught duration. And if you want, you can do the integration from here to here. That one also you have T naught. Okay. You can do the integration from here to here. Okay. From here to here. No, it should be from here to here. No? Okay, from here to here. Yeah, from here to here. That one also you have T naught, complete T naught. Okay. So any duration you can select. Okay. So I am selecting this 2 point from here to here for convenience. Okay. So I will not get any confused. Okay. So that I will not get any confused. So I chose my integration from 0 to T naught, from here to here. So here we have T naught duration. Okay. So Ck is equal to 1 by T naught. Okay. And we have to do the integration. Okay. So if you can see, okay, you can see that here within this period, you have two components. Okay. From 0 to T naught, xt is equal to a. Okay. From T naught to, sorry, from 0 to T naught by 2. Okay. You have xt is equal to a, but T naught 2 to T naught. Okay, so this is capital. Okay, I'm sorry. This is capital. T naught 2 to T naught, the xt is equal to what? From T naught to T naught, it is 0, no? It is 0. Xt is equal to 0. So you have two separate parts. Okay, so you have to do a separate integration for these two parts. Okay, so one is from 0 to t naught by 2, xt is equal to a t to the power minus jk omega naught t dt plus t naught by 2 to t naught. The xt is equal to 0 e to the power minus jk omega naught t dt. Okay, so these are the two parts you have to do the integration. Okay, but if you see this, if you consider this one, you can see that it is 0 into e to the power jk omega naught t, so that means it is 0. Okay, so here this term will be cancelled out, no, because it is 0. Okay, so you will have only this term to integrate. Okay, so I hope you get it. Okay, it is very simple. So ck is equal to 1 by t naught 0 to t naught by 2 a e to the power minus jk omega naught t dt. So we will do this integration. Okay, so can you tell me what are the variable of this expression? What are the variable? This t is a variable. This t is a variable, and this k is also a variable. No, k is minus, k can be 0, plus 1, 2, 3, 4, up to plus infinity, and minus 1, minus 2, minus 3, so on up to minus infinity. Okay, so this k also is a variable. Okay, so here you have two variables, k and t. Okay, but you are going to do this integration with respect to t. Okay, so you can consider this t is only the variable and this k is a constant. You can consider. Okay, so this k is actually a variable. Okay, but in this integration you can consider this k as a constant because you are going to do the integration with respect to t. Okay, okay, so we will do this integration. I think you know this integration. Okay, so if you consider e to the power, if you consider jx, if you integrate with respect to, let's say it is k, let's say, sorry, let's say it is alpha t. Okay, alpha t or something. If you integrate this with respect to t dt, what is the answer? It is e to the power alpha t divided by alpha. No, so this alpha is a constant. Okay, alpha is a constant. So e to the power alpha t, if you integrate e to the power alpha t with respect to t, you will get e alpha t divided by alpha. Okay, e alpha t divided by alpha. Okay, so here also you will get the same result. Okay, so you can see that ck is equal to 1 by t naught. Okay, so if you integrate, so this a is also constant, so you can get it out. Okay, no issue, a by t naught. Okay, and if you consider this one, okay, so here the variable we are going to integrate it with respect to t. Okay, so that means this whole terms is a jk minus jk omega naught t. This is a constant. So if you compare with this, so this minus jk omega naught is the alpha, no? Okay, the constant. Okay, e minus jk omega naught t is the alpha. That means it is the constant. So you will get e alpha t. That means e alpha is jk omega naught t alpha t divided by alpha. So alpha is here minus j k omega naught. Okay, so this is the result integration. Okay, okay, so if you can't understand, you can ask me. Okay, if you couldn't understand this integration, you can ask me. Okay, but I think it is very simple, you can understand it. Okay, okay, now the limit is 0 to t naught by 2. Okay, so we have to apply these limits. Okay, we also have to apply these limits. Okay, we also have to apply these limits to find the CK, to estimate the CK. So, okay. So, okay. So this jk omega naught t is a constant, so I can get it out here. Okay. So I get this jk omega naught t out. So I will have minus jk omega naught, and this t naught is here. Okay. And here, so I take these terms out of the bracket. Okay. And I will remain this one only. So if you first apply the upper limit, you will get e minus jk omega naught. Instead of t, you have to apply t naught by 2 minus c. Okay, so you will get e jk is 0, omega naught t. Sorry, jk omega naught. This t is 0. This is the variable. You have to apply this t 0 here. So you will have jk omega naught 0. Okay. So what is this? E to the power 0, no? So here you will get e to the power 0. Okay. E to the power 0 means it is 1. Okay. So you will have this term. Okay. So I think you can further simplify this. Okay. Because you know that the relationship between this omega naught and t naught, that is 2 pi by t naught is equal to omega naught. Okay. So t naught, so you can see that if you multiply it by this t naught and t naught, you will get omega naught t naught is equal to 2 pi. Okay. Omega naught t naught is equal to 2 pi. Okay. So anyway, I will do this in the normal way, otherwise you will get confused. Okay. So this omega naught is nothing but 2 pi by t naught. Okay. So if I substitute, I will go to the other line. So if I a minus jk, so omega naught is nothing but 2 pi by t naught, and here also you have t naught, and here you have e to the power jk omega naught is 2 pi by t naught, and this is t naught by 2. Okay, minus 1. Okay, so you can see that this t naught cancel out, so you will get ak as minus a jk 2 pi. Okay, and this t naught, and this two will cancel out. You will have e minus jk 5 minus 1. Okay, so this is the identity for ck. Okay, okay. So what you have to do is, now you can substitute the k value. Here you will have this k variable, no? So for this term, this k is a variable, and k is from minus infinity to plus infinity. Okay, so you have to substitute all the value, and you have to see what happened to this term. Okay, so let's first try to estimate the zeroth component, zeroth harmonic coefficients. Okay, so that is the DC component coefficients, no? So that is the DC component coefficients. That means C naught. Okay, so if you try to evaluate the C naught, okay, so let's say that k is equal to 0. That means C naught, your DC component coefficients. Okay, so it will be minus a j, k is 0 to 5. Okay, and you can see that e to the power minus j, k is 0, 5 minus 1. So this also will be e to the power 0. Okay, e to the power 0 means 1. And here 1 minus 1, you will have 0 here. And here also you will have 0. Okay, but this is not defined, no? This is not defined. 0 divided by 0 is not defined in maths. Okay. So you can see that once you do the integration, and if you try to find the zeroth harmonics component, okay, that means the DC component coefficients, sometime you will get undefined value. Okay, undefined value in mathematics. Okay, actually that is why we are separately find the zero component using that identity. Okay, what is the identity? C naught is equal to 1 by T naught within the T naught, that means 0 to T naught, okay, T naught by 2 xt dt. Okay, so that is why we are going to use this one, 0 to T naught. Okay, 0 to T naught xt dt. Okay, this one. Okay, this one. Zeroth coefficients. That means the zeroth harmonic coefficients or DC components coefficients. Okay. So if I do the integration, you can see that you have to do the two integration. One is from T naught 0 to T naught by 2. You will have A dt plus you will have to T naught. You have to do the integration from T naught by 2 to T naught. The xt will be 0 and dt. So that means this part is not available. Okay. So you have to do the integration. You have to find the integration only for this one. No, only for this one. Okay. T naught by 2 A dt. Okay. So if you integrate this, you will get a t from 0 to T naught by 2, and this 1 by T naught is there. Okay. And if you try to evaluate this, okay, T naught, 1 by T naught, this term, okay, and A instead of, and I think this A is also constant, so you can get it out, okay. So here T is only there. So now you have to substitute this upper limit and lower limit. So first you have to substitute the upper limit. So instead of T, you have to put T naught by 2 minus the upper limit is 0. So lower limit is 0. So it is 0. Okay. So you will have A T naught by 2. T naught into 2. So T naught cancel out. You will get A by 2. Okay. So the zeroth component, zeroth harmonic is A by 2. So this is the DC component. Okay. And you can also, so you have this identity. Okay, you have this identity. CK, I will rewrite here. CK is equal to minus A JK5 JK25 JK25. Okay, JK25 minus A JK25 e to the power minus JK5 minus 1. Okay, so you have CK, then you can find K is equal to 1. Okay, so that is C1. You will get minus A, J is 1. You will have 2 5. Okay, and minus J, K is 1, 5, minus 1. So this is C1. Okay, and also you can find the other first harmonic components also when the K is equal to minus 1. So it is C minus 1 minus A j minus 1 to 5, okay, e to the power minus j minus 1, 5, minus 1. So these are the first harmonic component, first harmonic coefficients, okay, harmonic coefficients. And likewise, you can find the second harmonic coefficients also when the k is equal to 2 and k is equal to minus 2, okay. So you will get C2 is equal to minus a, j, k is 2, 2, 5, e to the power minus j, k is 2, okay, k is 2, 5, minus 1, okay. And also you can find the minus 2 component, that is C minus 2, minus a, j, minus 2, 2, 5, okay. E to the power minus j, minus 2, this is j, minus j, minus 2, 5, minus 1. So on, you can find the third harmonic, fourth harmonic, all the harmonic you can find, and then you can substitute these harmonics to here. So here C naught, you will get, you get A naught A divided by 2, okay. And here you have a component, the coefficients, and this term is also there, omega naught t, okay. And here also you have a component and this term is there. Likewise, you can write this expression again, no? By substituting this calculated complex Fourier coefficients, okay. So you can just substitute it here, okay? So if you can do this question up to this level, okay, so you will get the full mark, okay. So if you can come up to this level, okay, if you can estimate this CK and if you can estimate this C naught, okay, then you will get the full full marks, okay. So actually sometime, okay, sometime the all harmonics are not there, okay. 0, first, 2, 3, the whole harmonics are not there, all harmonics are not there. So sometimes DC harmonic is not there, okay. So for some signal DC component is not there, okay. And maybe first harmonic and second harmonic can be there, okay, only can be there. Or the 2 and third harmonic and second harmonic may be there, likewise, okay. So we can't say that all the harmonics are there, okay. Some signal has limited harmonics, okay, and some signal has infinite harmonics, and sometimes all harmonics are not there, okay. If you want, actually, if you can do this question up to here, it is okay, okay. But if we see further, the harmonics are available or not, okay. So we have to simplify these terms, okay. So you can see that C naught is A by 2, okay. So it is available, no? A by 2 is available because A has a value and it is divided by 2. That means there is a value, defined value is there. It is not 0, it is not equal to 0. So C naught is available, okay. So if you consider C1, okay, if you consider C1, okay, it is minus A J 1 to 5 e to the power minus J5 minus 1, okay. So this is the first component, okay. So if you consider, okay, if you consider sine and cosine signal, so this is the sine signal, okay, and this is the cosine signal, okay, and this is 5, this is 2, 5, this is 3, 5, this is 4, 5, this is 6, 5, so on. So here it is 5, this is 2, 5, this is 3, 5, this is 4, 5, this is 5, 5, so on. Okay. So you can see that this is sine. So you can see that sine 0, sine 5, sine 2, 5, sine 3, 5, sine 4, 5, sine 6, 5, all are 0. Okay. So sine 0, sine 5, sine 2, 5, sine 3, 5, all are 0. Okay. All are 0. But you can see that the cos 0 is 1. Here, cos 0 is 1. And cos 5 is minus 1. Okay, this is the value, minus 1. So this is 1 and this is minus 1. And cos 2, 5, this point, it is again plus 1, no? Cos 2, 5 is 1. And cos 3, 5, it is minus 1. Cos 3, 5, it is minus 1. Cos 4, 5, it is 1. Okay, and cos 5, it is minus 1. Okay, so cos term is repeating, no? 1 and minus 1. It is oscillating between 1 and minus 1. Okay, so you know that this is a complex exponential part. Okay, so this part you can write it as cos 5 minus j sine 5. Correct? Okay, so you can say that sine 5 is 0. So this is 0. Cos 5 is minus 1. So this is minus 1. So e to the power minus j5 means minus 1. So you will have minus 1 minus 1. You will have minus 2. Okay. Then the C1 is minus 2 into minus a. You have 2a j25. Okay. So you have C1 term. Okay. And if you're going to calculate C2 terms, okay, so it is likewise like this, j225 e to the power minus j25 minus 1. Okay, so again you can write this term as cos 25 minus j sine 25. Okay, in the same way, sine 25 is 0 and cos 25 is 1. Okay, this is 1, not minus 1. So 1 minus 1, you will get 0. So you will have 0. Okay, so you can see that when the cos 5 is minus 1, you will have a coefficient. And cos k5 is 1, you will get 0. Okay, so for k, okay, for k is 1, 3, 5, you will get minus 1 for cos. Okay, so consider this. This is 1, 3, 5. You will get minus 1. K is equal to 2, 4, 6. You will get plus 1. Okay, for k even odd value, you will get minus 1. K even value, you will get plus 1. Okay, so whenever you get plus 1, the coefficients, you will get 0. Okay, so you can say that when the k is even, okay, even, the coefficients is 0. Coefficients are 0. So that means there are no harmonics for even k. Even value of k, there are no harmonics. All are 0. Okay, but for odd harmonics, if you have odd k, there are some harmonics. Okay, so you can see that. Okay, so that is the additional one. Okay, if you couldn't understand it, that is one. Okay, that is okay. So you can see that. Okay, this term is available. Okay. And this one, odd, the C1, K is odd. Okay. So this one and this one is available. First harmonics are available. And this K is even 2. Okay. So this is 0 and this is 0. So these are not available. The second harmonics are not available. Okay. And if you consider this 3, okay. So 3 is odd value. That means you will have a value here. Okay. You will have a value here and the third harmonics components are available. But if you consider fourth one, okay. So the K is even number. So you will get 0. Okay. So you will have only harmonics for odd value of K. Okay. You will have harmonics for odd values of K. Okay. So you can see that all harmonics are not there. Okay. So that is possible. Okay. All harmonics are not there, but infinite number of harmonics are there. Okay. So that is the idea you should get. Okay. So if you can try to find, so here we have only find 5 terms, 5 coefficients, 0th coefficients, 1 and -1 coefficients, 2 and -2 coefficients. And also you can try to find -3 and +3, -4 and +4 coefficients as a homework. Okay. So try to do that one. And I think it is better to try this one as a home exercise. Okay, please try to do this one. I think you can do this. The same format is there. Okay, same format is there, but few differences actually. Okay, so I think you can do this as an exercise in your home. So if you can't do this, you can ask me, then I can do this at the class discussion. Okay. So so first you have to verify this is a periodic signal or not. So you can say that this is you can see that this is a periodic signal and period is one circle is here. Okay. So the period is T0 from here to here, T0. Okay. So you can write that expression. Okay. Expression xt is equal to sigma k minus infinity to plus infinity ck e to the power jk omega naught t. You can expand this and write with respect to k. Okay. Then you have to estimate the ck and c naught. Okay. Ck and c naught. Okay. So to estimate the c naught, you can use that integration. Okay. 0 to t naught. Okay. Xt e to the power j k omega naught t, this is minus. Okay. And you can see that here also you have two parts. From 0 to t naught, you will have a. Okay. So when you are doing this integration, okay, from 0 to t naught, you will have a e to the power minus j k omega naught t dt. Okay. And from t naught by 2 to t naught. Okay. From t naught by 2 to t naught. Okay. Also you have a value there that is minus a e to the power minus jk omega naught t. Okay. So you have to integrate, you have to evaluate these two integration. In our previous case, this part is 0, no? But here you have to evaluate this part also. That is the difference. Okay. But I think you can do this. So please try to do this at the home exercise. Okay. Okay.